In this video, we begin a discussion on quantum theory and atomic structure. And given that we've covered half the chapters for the course, this is a good time to do a quick review of what we've learned. We're recognizing that we're halfway through the semester, but it's also an important breaking point. The topics that were covered in chapters 1 through 6 deal with ideas and concepts and material that scientists have really understood since before the early 1900s. It turns out it's very powerful information, very useful, and if you understand it and you're comfortable with the calculations and doing all the problem solving, you can work effectively in a lot of labs and a lot of even industrial environments, as long as you have the proper lab skills, which you'll need to develop, or the proper handling skills. But the calculations are good enough approximations that they allow you to handle a lot of common everyday occurrences in labs. Much of what we've seen, though, since it's really been known for so long, is based on macroscopic observation. It's not required fancy or complex instrumentation. What we've learned about so far is the structure of matter, that is the elements, compounds, mixtures, what they are, and the complexity of matter. We learned about stoichiometry, combining ratios, molar composition, molar mass. We learned how to name and write formulas for chemical compounds. And then we've also learned the general properties and classification of elements and compounds. We learned about periodic table and the periodic law. We've learned chemical reaction patterns for acids, bases, precipitation reactions, redox reactions. We learned about mechanical properties of gases. We've learned about energy flow and thermochemistry and some basic thermodynamics. This really covers a very wide range of important properties for chemical industry and chemical labs. Now, these are approximations that we've learned thus far, and there's another level of precision that's sometimes required, but there's sufficient precision here to handle most situations. The second half of this semester, I kind of term myself, for entertainment's sake, Adventures Through Inner Space. You likely probably did not ever ride on the Adventures Through Inner Space, but Disneyland out in California used to have a ride called Adventures Through Inner Space. And back in the late 60s and early 70s, when you needed a ticket to get on every ride, that was the one ride or one of the couple of rides in the park that did not require a ticket. It was sponsored by the company formerly known as Monsanto. There's a YouTube video here to show you what it shows, but it's basically looking at the internal structure of matter, which is kind of fun. And it gives you a picture of how people, at a theme park, visualize things a long time ago. It's also a time when people took science a little more seriously and enjoyed it. So what are we going to do in this half of the semester? Well, we're going to study atomic and molecular structure, and we're going to build some more complex models. And these models, to the extent that they're useful, are going to be able to explain what we've learned thus far, and will also help us to understand things for the future. It will turn out that this understanding of molecular structure will be really important when you get to organic chemistry. So here's our overview for this video and the Chapter 7 videos that we're going to go through. This video will go through the nature of light and some crucial experiments that help us to understand the structure of light, the structure of electromagnetic radiation, and its interaction with matter. Then we'll continue on with atomic spectra and atomic structure, the wave-particle duality of both matter and energy, and then we'll finish up with a real basic, we'll call quantum mechanical model of the atom. As we start off, we're going to look at the wave nature of light. Light is a type of what's called electromagnetic radiation. We don't have time to go into details on electromagnetic radiation. In physics, you would get a lot more information on this, especially in upper level courses and advanced chemistry courses. You will get a lot more information on electromagnetic radiation. At this point, it's just sufficient to say that electromagnetic radiation is a wave. That's one of its properties. It's wave-like, and as a wave, it has three key parameters that help us to understand its interaction with matter. The first one is waves, like sine waves, have a frequency. And a frequency is visualized as if a wave is passing through a plane in space, that plane would see a certain number of maxima in the wave per second. And the number of maxima, or equivalently the number of minima, that it would see would be equal to the frequency. That's the number of cycles per second. Waves also have a wavelength. That's the distance between maxima, or the distance a wave travels in 1 second. Those are equivalent definitions. Finally, the wave has an amplitude, and that is the height of the wave crest, or the peak. And you can express amplitude a variety of different ways. You can express it as the height or the depth, or you can express it from the height to the depth. So that's the amplitude. Waves also have other properties like phase and polarization that we will not consider in this class. Now, the speed of light, or more generally, the speed of electromagnetic radiation, turns out to be a constant in vacuum. This is a universal constant. It's one of the most important constants in science. So we call this C, constant C. It's its own letter. And just like any wave, the speed of light is its frequency times its wavelength. And the speed of any wave is its frequency times wavelength. And for light to 3 centimeter figures, it's 3 times 10 to the 8th meters per second. That's a number with its units that you should remember simply as a scientist or engineer. This is a number that everyone should know because it's such an important constant. You won't use it that often. We'll use it in this class, but it's just an important number to know as an educated person. Now, the one thing to note, this is in a vacuum. It turns out in other media, the velocity of light, or for translucent samples, electromagnetic radiation in general, is given by the speed of light divided by what we call the refractive index, n sub d. The refractive index is a constant. It's greater than 1, it's close to 1 for air, and it's equal to 1 in vacuum. And because of that, then the velocity of light in other media is less than 3 times 10 to the 8th meters per second. In air, to 3 centimeter figures, it is 3 times 10 to the 8th meters per second, but in water, it's less. In glass, it's reduced, and so forth. And refractive indices are found in tables. They're tabulated values that you won't see in your Gen Chem book, but they're readily available. So looking at the wave in graphical form, we see this here. We see 3 different waves, the red one, the yellow one, and the blue one. And the red one has a long wavelength, the yellow one has a medium wavelength, and the blue one has a small wavelength. And since the speed of light is a constant, then as the wavelength goes up, the frequency must go down. So the first wave would have a long wavelength but a lower frequency, and then the bottom one would have a small wavelength but a high frequency. And so since C is a constant, lambda goes up, nu goes down, or if lambda goes down, nu goes up. Here is a view on the amplitude. The amplitude of the wave tells us really about the brightness or the intensity of the wave. That's what we're learning from that. That's the parameter that ties together an observable with the underlying structure of light. So we'll find out that the frequency is related to the frequency, or corresponding to the wavelength, is associated with the color of the light, and then the amplitude is the brightness. Here are the regions of what we call the electromagnetic spectrum. So we know now that the speed is constant, therefore the wavelength and the frequency are correlated to one another. For light, if you know one, you know the other. And you can see on the upper gray bar, the upper gray figure, are all of the various regions of the spectrum. You can see that the wavelength of electromagnetic radiation can vary anywhere from under 10 to the minus 2. In fact, it can go down to 10 to the minus 3. It can be down as low as a picometer. But the wavelength can also be very long. It can be very, very long. It can be a kilometer in length, and that's for radio waves. And correspondingly, the frequency then, for those shortest wavelengths, the frequency can be up to on the order of 10 to the 20th, what we call hertz. That would be, a hertz is a reciprocal second, or a number of cycles per second. That's the unit on frequency. And you can see that the highest energy rays are gamma rays. That's they're from nuclear processes or in cosmic radiation. There's X-rays, which are the next step down in frequency. X-rays, you may have had an X-ray taken. Those are higher, what we'll see in a moment, higher energy, higher frequency. Then ultraviolet rays. Then a really small band in the middle is the visible region. And you can see as we blow up the visible region, the shortest wavelength is the violet end, and the longest wavelength is the red end. So if you go from red, orange, yellow, green, blue, indigo, violet, you're going from long wavelength to short wavelength. Next up would be infrared in terms of getting longer wavelengths, then microwaves, then radio waves. Now, given that light is a wave, waves show particular types of behaviors. If we look on the left side of this figure, we see wave, and up in panel A, we see light moving from air into water. And as soon as it meets the water, it changes its angle of direction and begins straight line motion in a different direction. The reason it does this is because light has a higher speed in air. The refractive index of water is higher, therefore the speed is lower in water. And as the wave hits that edge, it slows down and begins moving in a different direction. If you've ever gotten in a pool during the summer, you may have seen this behavior. If you're underwater and you look up, you'll see the location of people is different when you're looking at them underwater, because the light rays that have reflected off of their body and are coming to your eye get bent when they hit the water surface. And it turns out if you go look far enough down the pool, you'll see it looks like a mirror at the far end, because you've reached the angle of total internal reflection, which we don't have time to cover in this course, but we'll cover that in analytical chemistry and the upper and instrumental chemistry in the upper level courses. So we can see the wave bends when it hits a discontinuity in refractive index. In panel C, right below it, you can see waves when the black line in the middle represents a barrier, and there's a small opening in the barrier. So if a group of waves hits that barrier, then the waves bend around the barrier. And you've experienced this. So imagine you're sitting in a room and the door is open, and you call out to your friend. The sound waves will bend around the edge of the door. So even if your friend is not standing right in the doorway, they can hear your voice, because the sound waves will, what we call, refract around the barrier. So they refract around the edge of the barrier, and the waves, based on Huygens' principle, they will propagate out in all directions. Now you can contrast this with particles, and we'll see it's important to understand the difference between waves and particles later. Particles, when they hit a barrier, they slow down, but they do it in a gradual way rather than having a complete, change in direction that is maintained. And you can also see if you have a barrier and you throw particles through a barrier, they don't bend around the edge, they go in straight lines. So particles move in straight lines, waves behave like waves and bend around the edge. So if you look at C and D, you can imagine this in a macroscopic way. I don't know if you ever had a BB gun or played around with BB guns when you were a little kid. You can get one of the pump BB guns like a Daisy or one of the Crossfire BB guns. You pump it a few times, and then you go around chasing each other and shoot each other with the BB gun. It's not fast enough to penetrate the skin, so just play a game. So if you're chasing your friend, and let's say you chase him nearby a garage and the door's open, and they hide behind the edge of the door, you can't shoot them with your BB gun. If you shoot it, the BB will go straight ahead and it will miss them. But then you might yell out to your friend, "Hey, come here, I want to tell you something." And if they pop out in the door, then you can shoot them with a BB gun. But even when they're hidden, you can shoot them with your voice, because the waves coming from your voice will bend around the edge of the corner. So particles and waves behave very differently. We'll see some interesting quantum phenomena in subsequent videos. Now, waves also do something called diffraction patterns. So on the left-hand side here, you see orange wave fronts coming through, and each of these red line or orange lines represents a maximum in the wave, and then between them you have a maximum and a minimum. And these waves hit the black barrier, and that black barrier has two openings. It says two adjacent slits or two holes in the barrier. So each of those holes then will get a spherical pattern of waves coming out. Waves, when they interact with one another, can do something called constructive or destructive interference. In the center panel, you can see the orange waves added together. So in the upper panel, we have waves, it says, are in phase. That means the maxima are at the same location and the minima are at the same location. Whenever you add waves, you just add them arithmetically. So they add together. So if you had two waves of equal amplitude, you end up with a resulting wave that's twice as big as either one. But in the lower panel, you can see what we call out-of-phase interactions. That is, you have two waves interacting. One has a maximum where the other has a minimum. And conversely, one has a minimum where the other has a maximum. And what they end up doing is they end up adding up to zero, because one is negative when one's positive, and then one's positive when the other is negative. They cancel one another out. And you may have experienced this with sound waves before. You know, if you're in an auditorium and there are two speaker banks on either side of a stage, if you walk through the room, you'll hear loud spots and quiet spots. The quiet spots are where the waves are out of phase and you've got destructive interference. The loud spots are where you have waves that are in phase and they produce a summative effect. You have the same thing in noise canceling headphones. They take the sound that you're getting from the outside, they produce a wave that is exactly out of phase so that your ear experiences no sound. So what happens then at a long distance? Let's go back to our picture on the left-hand side. You see those circular wave patterns coming out. If you take a barrier at some distance, that barrier will show bright spots and dark spots, just like when you're walking through that auditorium. The bright spots are regions of constructive interference. The dark spots are regions of destructive interference. And in the far right panel, you see a water pool where waves have been created, and you can see the constructive and destructive regions. Now, another property of waves is what we call its energy. And this is leading us into something called black body radiation. It turns out that any solid object emits radiation. Now, if it emits radiation that if the body or the object is heated over 1,000 Kelvin, then you begin to see visible light. This is like when you turn your stove burners on. If you turn it up high enough, you start to see a red color come out. That is black body radiation. Any hot object can undergo this sort of radiation. And it turns out the color of that changes as the temperature changes. So if you go to a hotter object, it goes from a dull red to a brighter red. And if you get it hot, it starts to get orange. It'll even start to turn yellow or maybe whitish color. And if you have something that is very hot, then you can have something that gives off blue light or violet light. It turns out the color is related to, as we know, the wavelength or the frequency, because we're getting electromagnetic radiation. And it says the temperature is related to energy, but it turns out your wavelength is also related to energy. And since the wavelength is related to energy, the frequency is related to energy. So we have an equation, and this is something we'll call Planck's equation. He was the first to come up with modern physics, the first step into the world of modern physics with a variety of scientists. And it turns out the energy of a wave is given by the following equation: E equals NH nu. This is an important equation, and you will use this in your ALEKS homework and recitation and on your next exam. And here, n is an integer. A lot of times, n is simply equal to 1. It's a positive non-zero integer, so it's typically equal to 1, but it can be a multiple of 1. And h is a universal constant. It's called Planck's constant. We'll see what the value is later on. It's going to be in units of energy, in joules, multiplied by time, seconds, and the seconds are there to cancel out the nu, which is in units of 1 over seconds. So the answer should come out in joules. N has no units on it, so Planck's constant is 6.626 times 10 to the negative 34 joule seconds. That's an important constant. So what is black body radiation? Well, it turns out all objects are black bodies, even ones that are well below 1,000 Kelvin. They're just giving off infrared or lower energy radiation. But in general, heated objects radiate energy. So if you look at, coals or embers in a fire, they glow and they appear. The glowing kind of changes as you get thermal fluctuations in the system. Those are acting as a black body. The heated element, like the cal rod burner, if you have an electric stove, that burner element is a black body radiator. The old school light bulb filaments are black body radiators. When you have a piece of tungsten wire and you run a lot of current through it and it glows, all of these are black body radiators. Now, why do we care about these? Well, it turns out that people recognized, in the 1800s that atoms were what composed structures, and people even had estimates for the sizes of atoms, roughly. And based on that, they developed models to describe, as a function of temperature, they used thermodynamic models to describe how much radiation should come out of a black body at different temperatures. Now, on this graph here, in the left side, you see intensity on one side, that's the amount of light coming out, as a function of wavelength. So these are spectral plots. The blue, green, and red show a black body. This is a classic black body. It turns out, regardless of the material, if it behaves like a black body, you get the same curve. And you can see at high temperature, the 5,000 Kelvin, you get the blue curve because it's shifted to shorter wavelength. And as it cools down to 4,000, you get the green curve. And as it cools down to 3,000, you get the red curve. So those are the black body curves, and those were well understood. And people tried to describe this using particles and forces holding together particles, and you get the black curve if you try and fit a 5,000 Kelvin black body. So there's something called the Rayleigh-Jeans law, and that's the classical behavior, and it agrees with heated solids at very long wavelengths, and that works pretty well, but it fails terribly at short wavelengths. The graph blows up going into the ultraviolet region. And as it says in the red, they termed this the ultraviolet catastrophe. That is, in the ultraviolet region, down below 400 nanometers, the equations blew up to infinity. So they were just crazy. So the classical models of atoms in structures used to describe black body radiation failed terribly. So along came a physicist named Max Planck, and Max Planck, who, by the way, was told not to go into thermodynamics because it was all understood and nobody cared about it anymore because, the scientists always want to be on the cutting edge. He decided to go back into thermodynamics anyway when he began his studies as a student, and so he worked on the black body radiation problem. And he did one simple thing and then built a formulation around that. He proposed that the oscillators in the solid could only hold and then absorb or radiate specific frequencies. They couldn't simply give off any energy. Now, that may seem like a simple idea, but it's also like saying, imagine that your car can only hold exactly 1/4, 1/2, 3/4, or a full tank of gas. You can't put in a different amount. And you say, well, I'll just put in less. Well, what he was basically saying was the gas tanks of atoms cannot hold these other energies. It's not possible. He didn't explain why, but he said it has to be quantized. And by doing this, he got a mathematical formulation that fit the real black body curves. So he was able to match the experimentally observed black body radiator curves, which was a very profound thing based on this simple idea of quantization of the oscillators. And that one concept is going to lead us really through all the rest of this year, and it will take you through all of your more advanced physical chemistry. You quantize the oscillators, and we'll see why this quantization occurs, at least conceptually, later in this chapter. So the quantum theory of energy tells us that any object, and this includes atoms, can emit and absorb only certain quantities of energy. It can only hold certain amounts of energy. Other amounts of energy, it simply won't hold them. Energy itself is quantized. It occurs in fixed quantities rather than being continuous. So if you think about this, this was really the next wave. People, in long ago times assumed that matter was a continuum. And then, of course, with Dalton's atomic theory and all the chemists' work, people realized, no, there's the smallest unit of matter. The smallest unit of matter then would define how a structure behaved. Well, with Planck and then subsequently with Einstein and Bohr, they said the same thing occurs with energy. Energy is quantized. And it can only exist in fixed quantities rather than being a continuous tunable variable. Each fixed quantity of energy then is called a quantum. An atom changes its energy state by emitting or absorbing one or more quanta of energy. That's whether it's in a solid or a gas. And we'll see this in a little bit. So delta E then is equal to delta NH nu when you're going between various energy states, and N can only be a whole number and a positive value. And then we have Planck's constant, which we said before, 6.626 times 10 to the negative 34 joules times seconds. And then nu would be in 1 over seconds. So the seconds cancel and your result is in joules. You don't need to remember that constant, but you should have it available to you because you will use it on your next exam. The next experiment that helped to fortify this and built a kind of a new perspective was what's called the photoelectric effect. So there was an experiment that was carried out that it was not understood why the results were occurring the way they were, and it was Einstein who formulated an explanation for this based on quantization of electromagnetic radiation. And the experimental setup is shown on the right here. You have an empty tube, it's called a vacuum tube. And in this vacuum tube, you have a piece of metal, you have a metal plate, and then you have what we call a collecting electrode. That's the rod that the yellow ball is headed towards. It's a rod where electrons can come off the metal plate and get over to the electron, get over to the rod and then carry current. So of course, if this is in the dark, Metal is not in contact with the rod, and so the electrons can't fly through free space unless they're given some energy, so nothing happens. Down below, you see a battery, and that applies a potential, but you see no current flow because electrons can't get across the gap. Now, if you expose this to light, so if you put it out in the room, you'll see currents start to flow because electrons come off of the metal and then it can fly through the space and then get collected on the electrode rod and then pass through the circuit. So you can think of the metal as being oxidized, right? It's losing electrons. Now they regain them as they come up through the completed circuit, so the metal doesn't tarnish. But that's the way we can visualize this. The important result here is that only short wavelength light causes the electrons to be ejected from the metal's surface. The long wavelength light, regardless of how intense or bright it was, didn't work. So if you had a very bright red light, it still puts out a lot of heat. And there's a lot of energy there, but somehow that energy can't translate to get the electron off the surface. And you can have blue light, you can have even low intensity blue light, which is not all that much energy, but that's able to get the electrons to hop off the surface. So this is where the conundrum came in. So the solution here, we'll see at the bottom of this slide, is that light is quantized in packets. These packets were termed photons, just like we had quanta for these electromagnetic quanta. The waves are now particles. That is, light is now a particle, which is really the amazing piece. And the interesting part, if you know a little history on science, it turns out Newton, who worked on light centuries before, and of course Newton developed our understanding of mechanics, developed calculus, along with Leibniz, and developed our understanding of optics. He actually proposed what he called corpuscular or particle theory of electromagnetic radiation or of light. But that hadn't been said. It was, no one bought into that. This was what really helped to understand this. And the figure up above helps to illustrate this. So the stopping potential is the voltage, and that's the voltage going in the opposite direction to keep the electrons from coming off the surface. And so you can see that if the stopping potential is 0, then as soon as you hit the right frequency, the electrons start to come off the surface. And metal A would be something that would have a lower, what we call work function, or a lower ionization energy. For example, a metal that might lose electrons more easily at lower energy might be something like sodium. Whereas metal B, which is harder to lose electron, might be something like maybe gold. So that makes us think back to chapter 4. And so now let's take metal A. If you're at low frequencies, you get no electrons no matter what. And then when you hit frequency nu 0, the electron intensity starts to rise up, and you need higher and higher stopping potential as the frequency goes up to stop those electrons from coming off. Metal B takes more energy. You have to get all the way up to nu 0 before it starts to eject electrons. So the key, if the light frequency is low, no photoelectrons are produced, regardless of the light intensity, and that's up to what we call the nonlinear limit, which is beyond our discussion. But under normal light intensities, you see no electrons coming off. The conclusion, then, like we said before, light, that is electromagnetic waves, is quantized into packets. Here's a further discussion of experimental results. You can see on the bottom, this shows the amount of current as a function of light intensity, and this is for a wavelength that ejects electrons. So the more light you have, the more current you get. If you go down to the figure on the right-hand side, you see the repeat of what we just saw on the last slide. That is, the voltage required to stop the electrons as a function of the light frequency. And you can see that cesium, of course, has the lowest energy required to lose an electron. Lithium is next, and silver is quite a bit higher, and gold will be further yet. So that concludes our basic discussion of electromagnetic waves. In our next video, we're going to begin tying this into interaction between light and atoms.